I should switch these. Last time we talked about the Fourier number, which x is over the square root of alpha t, where alpha is the thermal diffusivity of the material. And I mentioned that the solution to most transient heat flow problems in solids, okay, this doesn't apply to liquids or gases, because then you get convection going on and things get different, and the alpha value changes. But in solids, which we're often dealing with in a welding process, you can approximate it by the Fourier number. You can get a very close solution by just looking at that dimensionless number. Now, it takes some practice, and you got to figure out which of the three parameters, x, alpha, and t, you're looking for, and you have to come up with the other two. Or you can compare, you can have all three and compare x versus alpha t and see whether you're infinitely thick or infinitely thin. But in 90% of the cases, you're either infinitely thick or infinitely thin, and then all you need to know is that, you know, it's saturated with heat or it's not saturated with heat. It's just heated on the surface if it's not saturated. And that often answers the question from an engineering point of view. And you can always find some scientist who will solve the differential equation, particularly nowadays, computer codes that, you know, you just plug it in and it runs it for you. So today I wanted to go over, we've been pushing out from flames and arcs. I want to go over laser and electron beams, which are at the far end of the heat intensity spectrum, 10 to the 6th to 10 to the 7th watts per square centimeter. Turns out, as we said before, if you go above 10 to the 7th watts per square centimeter, you just start drilling holes. The material cannot carry the heat away fast enough. And it turns out, if you do this, before you get to the point where you're drilling holes, you can actually have a deep penetration weld and a high depth to width ratio. And we said you can get, well, the highest I ever know I've ever heard is the British Welding Institute, in like a 10-inch or 20-inch thick piece of aluminum, made an electron beam weld that had a depth to width ratio of 200. Actually, they didn't make a weld, they just penetrated a solid block of aluminum, and it had a depth to width ratio of 200. But we mentioned a couple of weeks ago that you don't want 200. You don't really want a depth to width ratio greater than about 10, because you're going to miss the seam. I mean, the seam is basically a flat interface between two materials, and if you've got a depth to width ratio of 200 or 50 or something like that, you have a little bit of angular misalignment, and you're going to miss the joint. Things won't be aligned. So typically you only want a depth to width ratio of about 10, and in fact, when you use these types of power densities, you're going to essentially drill a hole, and then the metal will flow around behind it. And you saw the movie from the Japanese Welding Research Institute from 1980 that shows laser welding on Pyrex glass and electron beam welding and how the metal flows around behind to fill in and solidify. Now, it turns out you cannot drill these holes in less than a millisecond, and it's because of the inertia of the metal. I mean, you can liquefy the metal, but typically it takes about 1 to 10 milliseconds for the metal to be pushed aside by the forces that are generated in this process. Okay, the forces are generated because you're getting evaporation of metal from the surface of the weld pool, and that you basically have a jet shooting off, and the reactive force pushes the liquid metal down and out of the way. However, it's got a certain amount of inertia, and the way I always describe it is if you're standing in a swimming pool, waist deep in water, and you slowly lower your hand into the water, there's no significant force against your hand. If you slap the water hard, the inertia of the water is such that you actually can hurt your hand if you hit it hard enough, right? The water acts like a solid. So don't paratroop, don't jump out of airplanes a few hundred feet above the water unless you have a parachute, okay? Because you'll hit very hard. Okay, and you might as well hit solid ground if you hit something fast enough because of the inertia. So it turns out that the inertial time constant of the liquid weld pool is something on the order of 1 to 10 milliseconds. So you can't drill the holes any faster than that. If you tried to put the melting power in faster than that, you would find that all you do is ablate the surface. You just pieces of liquid metal just spew off the surface, and you just do a little bit of surface damage. Another concern is that you have to have the proper focus with your optics, whether it's electron beam or whether it's laser optics. You want to have a long focal length such that the beam comes in and can be focused somewhere down towards the bottom of the hole, typically, so that you can get nice parallel sides, or maybe even very slightly angled sides. And the reason for that is if you have a poor focal length, if you have a short focal length, which I haven't drawn that very well, but you'll generate most of your heat down at one area. You'll have a sharper focus there than up here, and that means you'll end up with a well pool that's pear-shaped or something. And if you do that, you're going to find that you don't have a good casting geometry. As the metal solidifies and shrinks, you're going to end up with voids here. And somewhere in my files, I've got a picture of that very thing. Okay. So laser and electron beam are nice processes. We mentioned before that they tend to go at very, very high production rates because of the high heat intensity. And that means they're used often in the automotive industry where you got to make tens of thousands of parts. Electron beam is used to make bimetal bandsaws. Bimetal bandsaws, you know, you've got a bandsaw blade, and if you can just put tool steel where the teeth are, the tool steel is much more expensive than the spring steel, which is the back of the thing. So they actually weld about an 1/8 inch wide strip of tool steel to maybe a 1/2 inch or 1 inch wide spring steel back using electron beam. So they're making thousands of feet of this weld, and basically the coils come off, go through a little chamber into the vacuum chamber, come out another chamber at the other side of the vacuum chamber, and just reel this stuff up, and then you cut the teeth in the tool steel, and you've saved a lot of, you've reduced the cost of your material. Laser and electron beam are also used in the aerospace industry, where the value of the parts is very high, and so you don't care about the fact you're using $1 million machine and you're only using it 2% of the time in terms to weld, because you want to make unique type of welds. Sometimes those are very small welds, because with very high heat intensities, you basically can get in and weld thin materials with relatively little damage. Sometimes it's to make a very deep weld, several inches thick, in a heavy piece of material without much distortion. If you start doing that with arc welding, you got these weld pool shapes that have a depth to width ratio of 1/2 or 1, and when they solidify, they shrink, and you get lots of residual stresses. So you can weld with laser and electron beam in heavy materials and not get a lot of distortion. And so that's important in a number of things like jet engines. But aside from automotive, well, I've seen data on it before. The automotive and the aerospace industry own something like 95% or 98% of all the electron beam and laser welders in the world. And then the rest are things like, specialized things like the bandsaw blades. It turns out there's a lot more lasers used now, not for welding, but for cutting. It used to be you'd stamp out sheet metal. You go into a small little, it can be a mom and pop shop, and you can buy a laser cutting machine now for $100,000 or $200,000, and might take up half the size of this room, but most of it's just table, and you put the sheet metal on there, and with computer numerical control, you basically can cut out in steel or aluminum sheet metal. You can do laser cutting and cut out the shape that you want. You can do one-off without fancy dies or anything else, and so it pays for itself in the savings in dies. And it's amazing. You go in a small little shop that probably doesn't do, you know, $3 million a year worth of business or something, which is not a lot of business for metalworking. But they've invested in a $100,000 or $200,000 CNC laser cutter for sheet metal. Okay, and they can do that all kinds of ways. I've got two little things to pass around. This is not a laser weld. This is a very small weld, but you, just by looking at it, I would not be able to tell you whether this was laser or arc welding. Turns out this weld is on steel foil. It's actually a business card of the company. They made it into a business card with the weld. But this is actually a plasma arc weld. And plasma arc, remember, can give you slightly higher heat intensities than regular old arc welding. When you get down to less than 10 amps in an arc, it becomes less stable. And so the plasma arc, the jet burner effect, helps stabilize that arc. And you can make very, very small welds with equipment that's only worth $20,000. But it doesn't matter. You can also make laser welds. You could do that with a $100,000 laser or a $250,000 electron beam machine. But that was actually done with a plasma arc. This next one is just a little, it's a prototype, but it's an aluminum tube and another end piece of aluminum, and it's got a little laser weld right here. Okay, just one weld. There's some crimps, and the laser weld is towards the short end of the tube, just ahead of those crimps. That piece was when they were trying to lighten the weight on military fighters. That basically was the explosive bolts for the ejection seat. It turns out on a military aircraft, you don't want to have your ejection controlled by your electrical system, because the reason you want to eject may be because you lost your electrical system. And it really hurts if you eject and you don't remove the canopy. You get a real headache. Okay, so it turns out, just like the space shuttle and some of the aircraft or some of the rockets, they have explosive bolts. And so the canopy is held on with bolts that have a little bit of explosive in them, and the ejection seat is also propelled by explosives to shoot. First the canopy goes off, hopefully, and then you shoot the pilot's seat out, and then he drops the seat, he's got his parachute right there, and he parachutes down. But basically it's a one-time use. So you got tubes of explosive charge that basically are the cables that set off these bolts. So when he hits the canopy release and pilot eject button, it turns out you basically ignite something, and it's a one-time, the signal is sent basically by a small explosive going down these tubes, just, you know, detonation line. And so they used to make them out of stainless steel, and that added weight to the aircraft, and so they decided they wanted to make them out of aluminum, and so they were trying to laser weld it, but it turns out aluminum's difficult to laser weld. That's actually not a bad looking weld. But aluminum is difficult to laser weld, and we'll talk about that in a little bit, why that's true. But this is a little explosives plant out in California, and I had to go out and visit them, and so they had their explosive mixing facility up on the hill. It turns out, I've actually seen data since then for explosive plants. The average explosive plant loses a building once every 4 years, okay? You can buy, well, so far as laser welders, there's not a lot of companies in this country anymore because they just didn't sell enough early on. There actually are a few. Out here in Sturbridge, Massachusetts, there's a company called Lasers Incorporated, and they purchased a lot of the other places. And so you can buy things there, but originally United Technologies and Avco were the ones that developed some of these high-power lasers under defense contracts. Avco Everett Research Labs, which is now a fleet bank over here in Everett, was where they developed the high-power lasers, and I went over there 25 years ago to look at one of these things, a 15-kilowatt laser. I could have had the original Mark I model that was sold to Caterpillar. It's because it didn't work. Okay, Caterpillar was looking for a tax write-off, so they offered it to MIT. Rather than having something the size of this room that didn't work, filling up space, I said thanks, but no thanks. I think they gave it to some other Midwest university. But in any case, those were research machines. There are some small companies who try to sell to companies like General Motors for lasers. But Lasers Incorporated is probably, out in Sturbridge, is probably as good as anywhere. A lot of the Japanese companies, the Matsushita, Hitachi, some of the spin-offs of the Japanese steel companies basically sell lasers, and in fact now a lot of these lasers, and also there's some Italians that trump lasers. So if you look it up in the Thomas Register, look up lasers, you'll find some high power lasers. But there's not a lot of these companies, and mostly the only thing that's kept them, the lasers guys going is basically these sheet metal cutting tools. So far as electron beam machines, it was Hamilton Standard, Pratt & Whitney, that in the 50s and 60s developed the machines, and I think Hamilton Standard still sells some machines. Siaki in Chicago, which was originally a French company that was brought over to the United States because they had a way to weld aluminum in the 1940s for the U.S. Navy in the Philadelphia Naval Shipyard, where they built aircraft in the Naval Shipyard. Siaki is out of Chicago, and they will build custom laser and electron beam machines and equipment. But Siaki likes to build for the automotive companies, and so they're building a $10 million turnkey system to weld one particular part. So it's not a big market for the equipment because it's very expensive as far as that goes. Does that answer your question? Okay. Okay, let's go through. A lot of people think that lasers and electron beams are basically the same and will behave the same and give me deep penetration welds, and so they're interchangeable. That's not really true, so the way I like to handle it is to contrast the two. And I've got about 8 or 10 different ways to contrast. And of course, with electron beams, I'm heating with electrons, whereas with lasers, I'm heating with photons. The thing that's important there is the energy of the electron beams is going to be on the order of, well, let's say 40,000 to 100,000 electron volts. Your machine's going to have up to 40,000 volts, or actually, yeah, up to 40,000 volts, or up to 100,000 volts or above. And there have been people who've welded with multi-megawatt, several million volt electron beams. We can talk about that in a little bit. Over here, the energy is H nu, and it turns out if I've got a CO2 laser, which is a high power laser at 10.6 microns radiation, the energy is about 1/10 of an electron volt. If I'm using a yttrium aluminum garnet laser, which is a solid state laser, also popular, it's 1.06 micron radiation, and it's about 1 electron volt. So 0.1 to 1 electron volt for the particles that are hitting the surface. So I've got about a factor of 1,000,000 in terms of the energy per particle hitting the surface. And why is that important? Well, it turns out this does subsurface heating, which I think is my second point. Okay? Yep, it is. Because of the energy difference, heat is deposited about 1/10 of a millimeter deep. That's about a human hair, right? It's not very deep. And this is all surface heat. And you say, well, does that make a difference? It turns out it does in some cases. Siaki, this company in Chicago, was not building a welding equipment, was building some laser hardening for the camshaft of automobiles. The camshaft has got these kind of little lobe-shaped cams on a rod, right? And as it rotates around, it pushes the rocker arms up and down, which opens and closes the valves on the internal combustion engine. Hey, does that sound reasonably correct to people who know something about engines? Okay, so I got these little camshafts going around, and these lobe-shaped cams, when they hit the rocker arm to move it, they're going to rub it up against that surface, and so you got a wear surface, and you'd like to harden that surface. And so a common thing nowadays is to use electron beam or lasers or electron beams to heat just the surface where you want it hardened. And it's quite common in automotive engine compartments now. I think there's a bushing that holds your power steering, and you don't want the bushing to wear out because now your steering leaks and the power steering fluid gets out. So they basically go inside this internal bushing, and with laser they just basically heat some stripes that hardens the steel, and so now you have some wear pads, these hard surfaces, that reduces the wear as the power steering is rotating inside this bushing. So there's all kinds of places in automobiles where people use lasers, electron beam. Well, on this particular camshaft problem, originally they built it as a laser because a laser is nice. You don't have to have a vacuum system, and we'll get to that. But it turns out they were looking at the fatigue life, and they were getting fatigue cracking within the design lifetime of the part, and that wasn't very good. And they ended up having to redesign the equipment and go over to electron beam. And the reason was just this little bit of deeper heating. You're only trying to heat or harden this top 2 to 4 thousandths of material. If you do it this way, the highest heat is right at the surface, and that is the material that expands during heating. If you remember what I talked about residual stresses, you get the exact opposite stress pattern after it cools that you had when it was hot. Well, the surface is in compression when it's hot, which means that the surface is in tension when it cools. That top surface expanded, deformed a little bit, never melted in this heating process, and this is just a surface hardening process. And when you cool back down, that top surface which deformed now shrinks the same amount, or actually shrinks even more than the surrounding material, but it had deformed when it was hot, and the material underneath it hadn't deformed. So now it has tensile residual stresses. The tensile residual stresses were leading to cracking, okay, fatigue cracking in service. You go over here to this process, now the maximum heat is 4 thousandths beneath the surface, and so that gives me compressive residual stresses when I'm all done, which is favorable for the fatigue situation. So two high heat intensity processes give you completely different surface residual stresses because of the difference in the energy of the particles that are hitting. If you actually go to 2 million or 10 million volt electron beams to try to, you can get deeper heating. You can get something on the order of 2 to 4 millimeters deep heating. And there are certain advantages to that. The disadvantage is the machine tends to cost you $1 million a bolt. Or just, okay, so if you're going $2 million machine, you're talking about just for the generator, $2 million bucks, and the rest of the machine might cost you another 10 million, so you could be talking a $10 or $12 million machine. But it can be done. In electron beam, sample must be conductive. And why do you have to have a conductive sample in electron beam? What happens if you were to hit electron beam against an insulator? It collects electron charge, right? If it collects electron charge, it doesn't take very much charge to build up, to act as a capacitor, and essentially you now start deflecting the beam. Okay, you now have a negatively charged surface. The electrons don't want to go there, so you lose your focus on your beam. So it must be conductive. Here, you can heat insulators. In fact, we'll see you can actually heat insulators even better with a laser than you can a conductive material. So far as making the material conductive, you can actually electron beam weld ceramics by preheating them. There were some studies done at the Naval Research Laboratory by a ceramist who's actually he's no longer there, but Roy Rice 15 years ago basically would preheat ceramics to 1,000 degrees centigrade, and lo and behold, there was enough conductivity in the ceramic at the high temperatures that the electrons would be carried away, and he's able to electron beam melt. Now it turns out, just because you can electron beam melt, I mean, most of the ceramics that you electron beam melt have little cracks running right behind the pool. So it's not exactly a good welding process because it is a cutting process as well as a welding process because of the crack that forms. But he was just trying to demonstrate whether you could do it. And there are a couple of ceramics that actually don't crack, but it's kind of specialized. I mentioned before, this requires a vacuum, and let's leave it at that. This is best in a helium atmosphere. Now, so far as requiring a vacuum, you have to have a vacuum to generate the electron beam. You do not necessarily have to have a vacuum to do the welding. There's something called out-of-vacuum electron beam welding. And basically you generate the beam inside a vacuum chamber, and you just have a little hole in your vacuum chamber with some aerodynamic windows, and you pump on this little hole from the side, and you can shoot the electron beam out into full pressure. So if you've basically got full pressure leaking in through this small hole that the electron beam's going out, but you're pumping on the sides of that hole, and so you can actually maintain a vacuum of maybe 1/10 millionth of an atmosphere where you want to generate your electron beam, and through this little baffle, series of baffles, this little hole, you basically pump the gas that's leaking in out. You pump it out as fast as it's leaking in. And that's great as long as everything's aligned. If not, then your electron beam ends up hitting your baffle and welding your baffle and melting it, and you have to replace baffles and stuff. But it turns out there is a company down here in New Jersey, not New Jersey, Connecticut, which actually is another company that sells electron beam equipment in this country. They used to be part of Lebel Heraeus, which is a German company, but they're now ETC, Electron Technologies Corporation or something. Anyway, I'm sure you'll find them in the Thomas Register. We used to go down there sometimes to use some of their equipment. They sell an out-of-vacuum electron beam equipment. And the reason they sell it is because there's a guy named Bert Schumacher, who, this German, who developed the out-of-vacuum electron beam with the baffles and stuff. He was hired by Westinghouse in Pittsburgh when Westinghouse was not in the broadcasting business primarily, but they actually, built nuclear reactors and things like that, and did research, and built electrical generators and things like that. See, Westinghouse no longer does that. They now, what do they own? CBS, okay, and they've sold off their nuclear division. I can't remember who they sold that to. And they sold off their power generation division to ABB or Siemens or whatever. Anyway, so they got rid of all their electrical generating capacity and quit doing research. So Bert Schumacher left there and he went to Ford. In all this process, he actually sold at one time, going back about 20 years ago, I think when he was still at Westinghouse, sold Ford about 20 or so out-of-vacuum electron beam welders to weld the stainless steel shells of catalytic converters on automobiles. I mean, catalytic, where they put the catalyst is just kind of a clamshell of two pieces of stainless steel, and you actually have a joint that looks like this. So here's your clamshells. Okay, this is catalytic converters in here somewhere. You've got these two pieces of stainless steel, and all you want to do is melt the edge. In fact, that edge is called an omega seal. If you look at the parts like this, and you melt that up here, it has the shape of the Greek letter omega. Okay, so they want to make omega seal welds in their sheet metal, and they want to do it very fast because they got to make a lot of these things, and gas tungsten arc will run maybe 6 inches a minute. Hooray, hooray. You'd have to have hundreds of the welding machines to weld all the catalytic converters, but they only needed, I don't know, maybe there's only half a dozen of these out-of-vacuum electron beams. So Ford touted this as great technology. Westinghouse and Bert Schumacher touted as great technology. Westinghouse closed their labs. Bert Schumacher went to work for Ford, which they needed him because if you talk to the people who actually ran the plant, all they had to say was cursing these machines because they were nothing but a maintenance headache for the same reasons I talked about. You're shooting the beam. I mean, anytime you got a vacuum system that's got a, an 1/8-inch hole in it, and a very high vacuum system with an 1/8-inch hole, that means your pumps are working pretty hard. But that's the way it's designed. And if anything goes wrong with the alignment of the beam, you end up melting your baffle and your hole's even bigger. So they were spending more time repairing these machines than they were making product. But it was touted as a great success. Bert Schumacher's retired now, but back 15 years ago, I wrote a review on electron beam welding in Japan, and he wrote this nasty letter to the welding journal where I published it, saying, why didn't I talk about out of vacuum electron beam? Well, first of all, the Japanese don't use it, and it was a review on Japan. But he wanted me to talk about all the great work he had done in Germany and the United States on out of vacuum electron beam. Which I responded that it was a review of Japan, and the Japanese don't use it. And so it didn't seem to me that I should be reviewing what he had done in other parts. Actually, I wrote a long letter, but the Welding Journal only published all of his letter because he was from Ford. But they only wrote about a half a paragraph of my response. And I was sort of irritated with the man. But anyway, and I asked the editor a couple years later when I saw him, I said, why did you only publish part of my response? He says, look, when you got someone on the ground, no need to keep kicking him. Okay? So anyway. However, when I say requires a vacuum, except for that, those silly out-of-vacuum electron beams that are at Ford, and a couple of other places in the world. I mean, they may have sold 8 machines in the world. But anyway, so it requires a vacuum. This is best in a helium atmosphere, and the reason it's best in a helium atmosphere is because with these types of power densities coming in on the surface and the metal vaporization coming up, you're now vaporizing these easily ionized metals. It's not hard to strip an electron off a metal atom. If I get electrons up in that plasma, or if I get electrons up in that vapor above the surface of that weld pool, I form a plasma, and plasmas will block the laser light. A free electron will absorb the light, and the last thing I want to do is generate free electrons. So it turns out you typically, in laser welding, if you're in the United States, you use helium. If you're somewhere else, you might use argon or nitrogen. But you have a transverse gas flow to try to blow aside the metal vapor and keep it from collecting up above here, because the metal vapor above here will defocus the beam that you're trying to get in here. If you can afford the helium, it doesn't take much. Typically, this is just a little needle of helium. You blow the helium across here, and since helium has the highest ionization potential of the inert gases, it will hold on to those electrons to higher temperatures than anything else. And so it turns out laser welding is best in a helium atmosphere, okay, because you can ionize either the argon or the air and generate free electrons and block your beam, okay? Another thing is you get 30% deeper penetration in a horizontal position. So if I'm welding from the top straight down, I will get 1 penetration, and if I turn everything 90 degrees and I make a weld from the side, I will get about 30% greater depth for the same beam parameters. And the reason for that is, if you remember, I'm forming a liquid layer around the sides of this, and as that, if I got gravity, if I'm doing a vertical weld or welding from top down, gravity will cause some of this stuff to flow and slump to the bottom, and I have to keep pushing that aside. If I'm in the horizontal position, if I'm welding and my hole is like that, it slumps down here, and I can keep drilling deeper and deeper and get about 30% greater penetration depth. Now, it turns out for lasers, you also get the same 30% deeper for horizontal, but I also get 50% deeper in a vacuum. You can weld with the laser in a vacuum, you just have to pay for the vacuum. You have to have a vacuum for the electron beam in general. You don't have to have it for the laser, which is a significant advantage. However, if you do try to laser weld in a vacuum, you will get about twice the penetration depth for the exact same beam parameters. And the reason is the same thing I talked about before. If you get this metal vapor coming up here and air up here, that will partially block the beam. It turns out you can get significantly deeper penetration for the same powers in electron beam than you can laser, because the low energy photons are more easily blocked by the gas vapor on the surface than the high energy electron beams. These 100,000 volt electron beams will just blast right through this layer of vapor on the top surface that's coming off, okay? But the laser photons don't do nearly as well, okay? So that's actually the next thing. Electrons penetrate the metal vapor, both on top of the cavity and inside the cavity. So you get deep penetration. With a 15 kilowatt electron beam, I can probably penetrate 2 inches of metal. With a 15 kilowatt laser, I may only be able to do a quarter as much, a half an inch or 3/4 of an inch or something like that. And here, I just phrase it as plasma decouples the laser. And as it decouples the laser, both with electron beam and laser, this decoupling on the surface will produce what we call a nail head weld pool. You'll get this with both electron beam and laser. Part of your main beam is coming down and is drilling that hole to the bottom, but some of it is defocusing up here in the vapor. And as it defocuses, you basically you melt the surface and get a nail head. So you've actually got two weld pools, if you will. One is a defocus pool, which is the top of the nail head, and the bottom is sometimes called the finger, pushing down through, and that's the primary beam. Any questions on any of this stuff? I'm going through it. So you see there's, the physics makes these things go quite a bit differently. Okay, so I'll leave that. Well, I guess I come over here and clean this up. So we got, what am I up to? 6, 7. Electron beam is nearly, not very clear, nearly, okay, 100% heat efficient. Typical values measured are 98 and 99% efficient in terms of how much heat is going into melting metal. And if you talk about raising the metal to temperature, how much is getting into the workpiece? Almost all of it gets into the workpiece. For ceramics, it's near 100% heat efficient on ceramics. It's on silver, copper, and gold, and aluminum. It can be 5 to 10% efficient. Basically, light's reflected by mirrors. Mirrors are things that have lots of free electrons. The metals that have the most free electrons are the ones with the highest electrical conductivity, which is gold, copper, silver. Actually, which metal has the highest electrical conductivity of those four? You might know? Silver. See, I always ask the question that's non-intuitive. Okay, gold has the highest thermal diffusivity, but the electrical conductivity, silver is the highest, has units of about 1.1 or 1.2 ohm centimeters, if I remember. Micro ohm centimeters. Copper is about 1.0. I don't remember what gold is. It's like 0.9, and aluminum is about 0.6. Okay, so among those four, silver is has about twice the conductivity of gold. In fact, during World War II, when there's a shortage of gold, because not gold, there's, it's always a shortage of gold. Everybody wants more, but the shortage of copper, because they were making the bullet casings were brass, right, and they needed copper for that. And during the Manhattan Project, they needed to, in Oak Ridge, they had to make these big magnets. And so they borrowed from the Treasury part of their silver stockpile, and they wound the magnets with silver windings. And this was all part of separating uranium They had these big magnets. So they had something like 200 tons of silver that they converted from. That was back when we used to have silver coins, and so the Treasury had a big stockpile of gold and silver. And they used the silver to wind the magnets, which actually made better magnets than if you had made them out of copper. And after the war, they actually had to give the silver back to the Treasury. But in any case. So it's because these have high electrical conductivity, lots of free electrons, they tend to just reflect the laser light. If I'm talking about iron, titanium, nickel, things like that, they're about 30% efficient as far as that goes, which is not too bad, but you're still reflecting 70% of the heat. And that's another reason why the lasers on metals don't give you the same depth of weld pool as you'll get with electron beams. You're going to lose 70% of your heat just by reflection, which can be a problem. Which is why if you go into a laser shop, they'll have all kinds of typically just simple plexiglass, sometimes smoked plexiglass, because it gives people a greater assurance to think that it's smoked and it keeps the light down. It doesn't matter whether it's smoked or not. When you're talking infrared radiation, the plexiglass stops it. Okay, but the using smoked plexiglass, so people think they're looking through sunglasses, is really just cosmetic. But in any case, lasers will not, infrared radiation will not go through simple little plastic plexiglass. Okay, it'll just vaporize it.
As far as the overall efficiency of the whole process,
yep.
Is the electron beam including its vacuum efficiency?
Oh, you're talking about overall? Well, yes, it is, but not. But it uses less energy. The vacuum consumes a fair amount of energy, but the main reason is the laser is only about 10% efficient at transferring total power to beam power. 90% of your power is just cooling the whole laser. Okay, so the laser costs more energetically, total, plug power, wall plug power. Actually, I'll pass a couple of these around. If you want to see what plexiglass or lucite happens in a laser, it actually is absorbed by it. This actually comes from Hitachi, and I can pass these around tomorrow, but if you hit plexiglass with a laser, you basically just vaporize. This is just a pulse laser, and you vaporize some of the plexiglass. So I'll probably pass these around tomorrow because I won't make them all the way around today. These I got from when I was, I think, at the Edison Welding Institute in Ohio, Columbus, Ohio, at Ohio State. And this is just, you're checking the beam shape of your laser. You just take a little piece of plexiglass and you blast it, and you just vaporize the plastic. So the plexiglass will stop things, the laser light reflection. It turns out there's other things you can do. 20 years ago, well, almost 20 years ago, maybe 18 years ago, I had someone from Johnson & Johnson that makes medical instruments. I've worked with them for 20 years down south of here, and he was coming by to talk to the people right down here in the physics department. Okay, the spectroscopy lab right over here in the basement, the building next to us. But he wanted to drop off a sample that I was going to look at, so he drops it off, and I said, well, what are you here for? He says, oh, I'm going to visit the physicist. I said, what? He says, what's wrong? I said, oh, no, never mind. He said, well, I'm going down to talk to him because we use laser surgery to cut. In this case, they were worried about the fallopian tube, but they do very fine cutting of things. The fallopian tube's a very, very small tube, and you don't want to. If you want to do surgery on it, you want to open it up. The doctor wants to open it up, but they don't want to cut all the way through. And so what they use is a little metal backstop that they put down part way down the tube, and they cut, and then they push the backstop up, and they cut some more. And so, and then if you try to do it with a scalpel, it's so flimsy, it just kind of moves around. So. The problem was when you do this with the backstop and with the reflectivity, they would burn other parts of the body. So whether you're talking laser surgery, eye surgery, or doing other types of surgery on the body, in this particular case it was, they do a lot of OBGYN type of instruments. So I said, well, okay, well, have a good time. Well, he came back 15 minutes later just shaking his head. I said, oh, so now you understand? He says, yes, I understand. He went down and he says, well, he wanted a metal that would absorb the laser light so it wouldn't reflect it and burn the patient where you don't want it burned, or the patient burned. And they said, well, all metals absorb light. And he says, well, yeah, but they don't absorb enough. Well, they absorb light. You know, to physicists, it was just a question of do they absorb some light or not. You know, they didn't care about how much. So we sat down. I said, actually, I guess I told him if he didn't get help from them, he could come back. So we sat down. He explained to me, and I now have 2 or 3 patents, which are probably about to expire. Basically, we came up with the magic material, anodized aluminum. Okay. In fact, I said to him that day, I said, well, you could use anodized, too bad you can't use anodized aluminum. He says, why not? We make aluminum instruments. I said, you do? Because I would have thought aluminum instruments would corrode and stuff. He says, no. So we went and did studies of aluminum and titanium and other things, because they use titanium instruments and stainless steel. And sure enough, you can measure 30% absorption on your nickel and your iron and your titanium, your stainless steel and your titanium, and you measure about 5% absorption on the aluminum. But if you anodize the aluminum, now I have a ceramic, right? So the top surface is about 10 microns thick, and we actually anodized to different thicknesses. I think we did 4, 6, 8, and 10 microns. And you get, as you get closer to the CO2 wavelength, you start to get to 100% absorption. With 4 microns, we were only getting about 50% absorption because it was shorter than the wavelength of the light. But if you put a 10 micron, which is about a half mil coating, actually 4/10 thousandths, on the aluminum, you have the good thermal conductivity of the aluminum to carry the heat out of the backstop, but you have the ceramic surface, which absorbs 100% of the energy. And we were able to hit these instruments with 100,000 watts per square centimeter, which is more you ever need, power density you ever need to cut tissue, without doing any damage to the backstop. Okay, so you could reuse these things, and now you had something. The surgeon had something that he can use as a backstop to, you know, essentially catch the photons after they've cut the tissue, and end up with a clean cut and not reflecting light and burning the patient where you don't want to burn the patient. So, you know, it's just understanding the basic physics, and you can invent things. I mean, it took all of about 5 minutes to come up with this idea. Now it took a little bit more time to, you know, develop the data and for the patent and stuff. But I mean, I bet there wasn't more than a week's worth of work. It probably took as long to work with the patent attorneys to write the patent as it did to do the work. Because basically, you just need to know that the patent basically says you're going to put a non-conductive coating about the wavelength of the laser on top of a highly conductive material. So if you've got some material, a coating, you could plasma spray on a ceramic coating on a piece of copper, and it would work even better because it's got better thermal conductivity than the aluminum. It'll carry the heat away quicker. So anyway, I'll finish up this stuff tomorrow. Okay, tomorrow's the last day, and we'll finish up laser and electron beam.